Well, here we are again, EET 260, and we're going to talk about input threshold voltage on our processors. We have just a digital microcontroller. It pretty much outputs ones and zeros, and it can read in ones and zeros. And we've seen how on output, if we pulse things right and low pass filter it, we can make what appears to be an analog voltage from a digital device. That's what pulse width modulation does. When we drive a motor or an LED or something which either operates slowly, like that capacitor in the low pass filter, or a motor, or our eyes operate slowly looking at the LED, we perceive to be able to control something at a level, even though it's really being controlled by a series of pulses. So as we kind of figured out how we could take a digital a number inside the microcontroller and drive it out in a way that sort of looks like an analog a level, a steady DC level outside. In our example, we needed to do some more filtering, but you got the idea. You could see the voltmeter sort of averaged things out and gave us a accurate reading, and if we had more filtering, our oscilloscope display would have floated up with a more smooth looking DC level than that kind of shark fin charge discharge waveform that we had. But you could see the DC level, so we had filtered out some of the signal. Now, going the other direction, you might ask, is it possible for us to make analog measurements in the outside world and bring them into a number inside the microcontroller? And there are ways to do this. Some of the first analog to digital converters, what they did is you built a current source in your microcontroller and you turned it on and you charged a capacitor. And if you do the mathematics, running a current source into a capacitor will make a nice linear ramp, like a sawtooth waveform. And if you compare your rising sawtooth to some other analog signal with a comparator circuit, then when the two signals are equal, when they switch, you can note that in your microcontroller, and you could have timed how long it took for that ramp to come up to the voltage in question, and made a determination of what that voltage was. That's called a single slope analog to digital converter, and they can be built pretty accurately, and some high-end voltmeters that are multiple digits, like say 6.5, 7, 8, 6.5, 8.5 digit voltmeters, use a technique called a dual slope integrating converter. And what you're doing when you pile that current into a capacitor, current is just electrons per second. It's charge per second, and capacitors are a bucket for charge. So if you can put the electrons in at a steady rate, then the voltage, which is proportional to the charge in the capacitor, that voltage will climb at a steady rate. And again, if you have some sort of trip mechanism like a voltage comparator, when you're linearly climbing capacitor voltage is equal to or crosses over the voltage you want to measure, your microprocessor could have timed the start of that charging of the capacitor to when its voltage crossed over your voltage to be measured, and you kind of do a little similar triangles thing there, and you can say, oh, I know what my voltage is because I know how long it took to climb up to that voltage with a constant slope increase in the voltage. Yeah, it's great to describe that kind of stuff with no diagrams at all, so we may go back there. But at any rate, we still have the problem of being a digital microcontroller and trying to come up with some way of measuring analog voltages. So let's try let's learn a little bit something about the way our digital inputs work. So this is all about digital input threshold, and in digital logic you have the transistor logic, TTL, which says that all your low voltages should be less than 0.8 volts, and all your high voltages should be greater than 2.4 volts. And you really shouldn't be hanging around between 0.8 and 2.4. That band is kind of a dead band, or a noise immunity band. And that works really well with digital logic. So transistor logic, or TTL, is actually a bipolar solid state technology. It uses bipolar junction transistors. MOS, or CMOS, specifically CMOS logic, like the famous 4000 series, or the variants that copy the 7400 TTL, like 74C, 74HC, 74HCT, 74LVC. It's just an alphabet soup of logic families. Some of those are CMOS and some of those are bipolar TTL. The TTL ones tend to have that 0.8 volt max input. Sometimes it's 0.4 volts, depending which family it is. And the minimum high voltage is a 2.4 volt input, sometimes 2.0 volts. I think I was remembering that incorrectly. But regardless, between 0.4 and 2.0, you've got that dead band, and that gives you good noise immunity. So transistor logic inputs, whatever they're implemented in, whether you can actually make them implemented in CMOS or make them with bipolar transistors. But if someone says that your digital input is TTL compatible, then it'll switch between a 0 and a 1 somewhere between, say, 0.4 and 2.0 volts. And we're going to find where that switch point is for our basic stamp, which designs its inputs to obey the TTL standard. If you look at some of the CMOS inputs, and some of the basic stamp microcontrollers have the ability to set their input threshold to either CMOS or TTL. CMOS tends to switch somewhere near half the supply voltage. So if you're in a 5 volt system, somewhere around 2.5 volts is the place where you stop seeing zeros and call your input a 1. Without further ado, let's take a look at a circuit we have here. Now I've got a potentiometer here, and I think it's a 10K. I forgot what it is, but anyway, I've got a potentiometer, and it's connected. One end of the potentiometer is connected to ground, VSS, or ground over here. The other end is connected to VDD, which is 5 volts. So so if I look at the voltage across there, it's very close to 5 volts. The other side of it is like 0 volts, and in the middle is the wiper, which forms a voltage divider, and that goes to pin 0 of my processor. And so by turning the potentiometer, sorry, my finger's in the way there. By turning the potentiometer, you know, the voltage in the voltage divider can go down as low as, well, 0, and as high as probably 4.98, maybe. I don't know if we get up there. And there we are, 4.98. So that works as it should. I'm in mid voltage right now. But let's go look at our sketch that's running right now and take a look at it. This sketch is really pretty simple, as you can see. We're using pin 0 as an input, and what we're doing is debug is to say, please print out something. And what I'd like you to print out using decimal is the value of this question mark means query input 0, print out its value in decimal, do a carriage return, and then, you know, keep going. And you know, if you don't like the carriage return, we could get rid of it, but that, you know, seems to be working. So if I go all the way down to, if I go all the way counterclockwise, hopefully you can see that I am, my input 0 is, the value is 0. And as I go up, and my meter is at, let's just show that, my meter is at 0 volts. Now, this is unfortunate that we have to go between here, but let's go up and we'll try to turn this thing upwards, and we'll try to get it to turn to a 1. I'm going to go very slowly. And continue to turn it. I got a 1. I'm back to a 0. There it is at 1, 0. Well, with just pressure I can change it. So now we're at 1. Let's go over here and look at what our meter says. Our meter says 1.422 volts. I think some of the basic stamp exercises say 1.4 volts. It's not going to be, you know, the most accurate thing, but that was the value for input P0. We can try a different input, like say input P8. I think that's input 8. Let me check here. Well, one way we can tell is to change our code and say we're going to, you know, input 8 is, we're going to use that, and we're going to ask for the value on input 8, and we'll send that down there. And it's a 1 now, and if we turn it back to a 0, look, just a little bit of pressure turned it to a 0. So maybe that is the same voltage. Well, 1.402, we had 1.422. These potentiometers are not the most accurate thing. You could actually get a 10-turn potentiometer, which allows you to measure these voltage in much less turning and get a sensitive measurement. But it shows that the input threshold at which our microcontroller says that pin is high or 1, or that pin is low or 0, is right around 1.4 volts. So there's our experiment, and we'll see you next time. But you know, there's a voltage comparator built into these digital inputs in essence, and it's you know, it's right around 1.4 volts. And I don't know what there is for hysteresis there. I don't think there is any. I think it's a straight threshold comparison type thing. So 1.4 is probably the number to remember for our future experiments, where we try to do things based on the threshold voltage. So we'll see you next time. Thank you very much, and take it easy.